I'm Professor Brad Fulton, and welcome to my Stats podcast. This is an edited audio recording of my course. Each lecture is its own episode, and there's a total of 24 lectures. This course provides an introduction to the quantitative methods social scientists and data analysts use to collect and evaluate empirical data about society. Through this course, you will learn to gather, describe, and analyze data with an emphasis on the application and interpretation of these methods. This course will also help you to be a more informed and critical reader of academic research, public opinion polling, and advertisement claims that present statistical evidence. Although some of the current events I reference might be dated, the content is timeless. I hope you enjoy this lecture, and if you have any questions, you can email me at bradrfulton@gmail.com. Hi, my name is Professor Fulton. If you like this podcast, you'll love the book I use for the course. It's titled Statistics, Unlocking the Power of Data. This book uses a highly intuitive approach to help students visualize statistical concepts, which accelerates understanding. I've reviewed dozens of textbooks, and Unlocking the Power of Data is hands down the best one out there, mainly because of its unique intuitive approach and straightforward explanations. You can find a link to the textbook in the show notes, and if you use the promo code BLOCK5, you'll get a 10% discount. This is the last of 4 on inference, looking at the normal distribution. So this is quantitative variables. Yesterday we looked at sample means, and so today we're looking at difference in means and then also correlation, which involves quantitative variables. Fortunately, all these things are going to be a repeat with slight variations. The way to calculate the standard error when you're looking at the difference of means is going to be standard deviation of the population parameter for your first quantitative variable over its sample size plus the population standard deviation for the second quantitative variable over the sample size of the second quantitative variable that you're looking at. And you'll remember the standard error for a single mean was just the standard deviation of the population parameter over the square root of n. So this basically accounts for the variation in both variables. The two formulas are related. And again, we don't know the standard deviation of the population values, just like in the previous examples. So then how can we estimate it? Because our sample is a random sample of the population, the standard deviation of the sample values, S1 and S2, provide good estimates for the population standard deviation. So in order to calculate standard error, we need to know the population parameter, the standard deviation of it. We don't know it, we can't know it, and so we do our best estimate, and our best estimate comes from our sample. Up here, you have standard deviation of the sample values is 5, so that becomes our best estimate for the standard deviation of the whole population. And so then our formula becomes like this, where it's substituting sigma for S. With just a single mean, the same for difference in means, that when we replace sigma with S, it changes the distribution of the test statistic from a normal distribution to a t-distribution. So like when we say the distribution of the test statistic, it's basically, what does this distribution look like? The normal distribution is like this, and the t-distribution is just slightly different. And it varies based on your sample size and degrees of freedom. So for a difference in means, the degrees of freedom for the t-distribution, the way you calculate it is the smaller of n1 minus 1 and n2 minus 1. So basically, whatever sample size is the smallest, that's the one that you're going to use to calculate the degrees of freedom. That's going to be your most constraining component. So it's just a matter of looking at those two values and what's the lesser, and that gives you the degrees of freedom. And then the two inferences that we make with our difference in means would be the confidence interval of our point estimate, also then hypothesis testing. So the first one is, this is the conditions that if n1 and n2 are large or the sample data are normally distributed, the confidence interval can be calculated by, again, this is same formula for calculating confidence interval. The things that change are, in this case, the t-star and then the standard error. It's a different formula that you use to calculate standard error, but the general formula is the same. And so our sample statistic is the difference in means, so it's x bar 1 minus x bar 2, and then plus or minus t star, and then this is our formula for standard error. It's knowing, okay, what is it that I'm measuring? What is my test statistic? And in this case, because it's difference in means, this is going to be our sample statistic, and this is the standard error that we use for it. As far as finding t star is a location on the t distribution with n-1 degrees of freedom, and its value is determined by the confidence level that's selected. So that's where, if you want to know what t star is, you go on to stat key, to the t distribution, and whatever your confidence level is, you do the two-tail, and what's the middle 90%, 95%, 99% of the values. So this is the same as what we've done before. And then similarly for hypothesis testing for a difference in means. So with hypothesis testing, we want to know the distribution of the difference in sample means, assuming that the null hypothesis is true. Like even in a homework assignment, it'll ask, what is the confidence interval for the estimates that you're making? Or it'll say, what is the probability that a particular value is greater than or less than a certain amount? And so it's a tip for you, am I supposed to do a confidence interval test, or am I supposed to do a hypothesis test? You can almost think of like confidence interval as looking at the middle of the distribution and what's the range of confidence that we have in our point estimate. And if you're looking at the tails of wanting to know, is there things as extreme as a particular value, you're going to do hypothesis test. With hypothesis test, the population mean for variable 1 minus the population mean for variable 2 is going to equal whatever the null value is, the null mean. And a lot of times that's 0, but not always. And then our test statistic is the same one, and since we're dealing with quantitative variables, we're using the t statistic instead of the z statistic. These are all values that we arrived at before. The test statistic is right here. It's the difference in sample means. The null value is right here, and then the standard error for your test statistic is right there. This test statistic gives you a value. It's a standardized test statistic. It's going to give you a value that then you need to see what is the proportion of values that are as extreme as that particular value on the p-distribution. And that's how we're calculating the p-value. So there's a lot of steps along the way, and at different times some of you stop at a certain step and say, okay, I'm done, I've finished the problem, but you actually have to carry it all the way through to get the p-value. So the first step is calculating the standard error for your test statistic. The next step is to calculate your standardized test statistic, and then the next step would be using that value to obtain the p-value. And the p-value, there isn't any formula you use. That's when you just go to stat key and look at where your t-statistic falls in the distribution. With the p-value, you can say we either reject the null hypothesis or we don't reject the null hypothesis. Oh, one thing that I noticed in the book and in other places that a hypothesis test using the t-distribution is often called a t-test. So like if in shorthand in the book they say, we conducted a t-test on the difference of means, you'll know that what they're referring to is a hypothesis test for a difference in means. So again, that's like another shorthand that you might hear, and don't be thrown off by like, what is that supposed to be about? So an example that applies both these things that we learned. Does anyone know what the Pygmalion effect is? All of you are a product of the Pygmalion effect, I think. So here it is. Teachers were told that certain children, chosen randomly, were expected to be super high achievers based on the Harvard aptitude test, a test that didn't actually exist. And the children identified as being super high achievers were selected randomly. So basically, they went into different classrooms and randomly selected a handful of students to be identified as being super high achievers, and then went to the teachers and sat them down and said, hey, we want to let you know that these 5 students in your class scored amazingly high on the Harvard aptitude test, and they are just super high achievers, and we just want you to let you know so that you can be aware of it as you're teaching the class. But in reality, these children were no different than any of the other children, or at least they were randomly selected from the population. So there was no prior information about these students. What they wanted to see was, are these students who are identified as super high achievers going to actually perform better in their class? And the way they measured it, performance, was the change in IQ over the course of 1 year. So they took the whole classroom, had them take the IQ test, got a baseline score, and then a year later they had everyone take the test. And so you have two groups. You have the ones who are labeled as super high achievers, and you have their IQ score at time 1, and then their IQ score at time 2. And what we measured was the difference in IQ scores over that time. And then we had our control group of all the other students who weren't labeled as high achievers, and we took their IQ test, and then we had them take the IQ test a year later and got their scores. So X is the change in the IQ over the course of 1 year. That's how the experiment is set up. Here's the actual statistics from the study. So the high achievers, there were 65 high achievers in the sample and 255 control group, people who were just students that didn't have any label. The sample mean, and this is the change in IQ score, the high achievers saw on average a boost of 12.22 in their IQ score, whereas the control group saw a boost of 8.42. And then the standard deviation for these sample values is 13.3 and 12.0. Does this data provide sufficient evidence to conclude that telling teachers that students are super high achievers will lead to an increase in students' IQ scores? We see that the difference in the change of mean IQ scores was 3.8, indicating that the super high achievers ended up performing better just because they were labeled as super high achievers. So does this provide sufficient evidence? How would you guys answer this question? What is 3.8? What's a word that could describe what that value is? Well, we're looking at means, so it's difference in means. It's a point estimate. What are characteristics of a point estimate? How accurate are they? It's always just a single number, and it's based off of a sample of the population. So this is our sample, a total of 320 people, but our population would be all children in all schools. And so we're basing off of a sample of 320. We say, when we ran this experiment, we saw a difference in means of 3.8. But that's just a point estimate. How confident are we that that would be true for the entire population? If we went and labeled 1,000 students super high achievers and did a larger experiment or a larger sample, would we get the same difference in means? Would it be close to 3.8? Would it be something completely different? It goes back to here. This is our test statistic, and it's X bar right here. And we want to know how much error is in that point estimate. We want to know how much does it vary, because we want to make inferences about the whole population. And so we have our point estimate, but we want to know, if we reran this experiment, what would our another point estimate be? It might be like 3.82. And if we reran it again, the difference might turn out to be 3.78. Each time we run the experiment, our sample statistic is going to vary slightly. What we want to know is how much variation is there going to be. So right now, this doesn't provide sufficient evidence because all we have is a point estimate. And so we need to either look at the confidence interval for our point estimate or do a formal hypothesis test and say, if there was no effect of being labeled a super high achiever, what are the chances that we would get a difference in means of 3.8 just by random chance if there was no effect? You could just look at this and say, yes, look, there's a difference, end of problem. Or I think some of you on the assignments have said you just sort of did a difference in proportions or a difference in means and you found that there's a difference, and so you said, yes, there's a difference. But you can't draw that conclusion. You have to see how much variation there is in that sample statistic, what the confidence interval is for that statistic. If you just stop there, if you just calculate the sample statistic, you can't draw conclusions from that. The ways then you could test to see if it's sufficient evidence The first is, it depends if we're sufficiently confident that the confidence interval for our point estimate for the sample difference in means, which is 3.8, does not contain 0. So if the confidence interval, like say we do a 95% confidence interval, if that interval doesn't contain the value 0, then we can be at least 95% confident that there is a real effect going on, that labeling someone as a high achiever will actually boost their IQ scores. Or it depends on how likely it would be to get a difference in means as large as 3.8 by random chance if the null hypothesis was true. Both of these are a way to test our point estimate to see if it's statistically significant, see if it's different from 0. So to answer the question on the previous page, we can either calculate the confidence interval or conduct a hypothesis test. We take the same approach with almost all the test statistics that we're looking at. So the first that we'll do is confidence interval. And so anytime you approach a problem, it's important to take all of your summary statistics and map them out so that you're clear what values you have. And often you'll have more information than what you need. You can't just say, okay, all the numbers that are in the question, I'm just going to need to plug them into my formulas. So it's important to know what each one is telling you. Just lay it out, something like this. So, and in this case, I should have put the degrees of freedom. You take the smaller of the two sample sizes. So in this case, it's n1, and you do n1 minus 1 to get 64. The first thing you do is check the conditions. And so these conditions, if they're met, they let us know that the distribution of the sample statistic is going to be a t-distribution. If the sample sizes are smaller than 30, then we can't use this approach of normal distribution. We'd have to use the bootstrapping. In some ways, that's why bootstrapping is better, because it's not limited at all by sample size. But most times, we're using samples that are larger than 30, so it's not a problem. Okay, and then the next step is to find the t-star for a 95% confidence interval. So t-star is the location on the t-distribution that's based on whatever your confidence level is. So how do we find the value for t-star?
Go to stat key.
Go to stat key. That's always, when in doubt, go to stat key. So you say go to stat key, Brittany, and then what? So then you go to the t-distribution, and what's our degrees of freedom, as Chris mentioned? Do you guys remember? 64. Okay, so this is what the distribution of the test statistic is going to look like. We want to calculate the 95% confidence interval. If I wanted to know the 50% confidence interval, how would I find t-star? So what we want to know is where the middle 50% of the values in this distribution lie. The lower bound and the upper bound. We can plug in numbers. We can use stat key to calculate it for us. You want to try, Tim?
Put 0.5 or 9.
Right here?
Mm-hmm.
So you do 0.5. So what that shows you is this is the middle 50% of the values. And so the confidence interval would be negative 0.678 to 0.678. And so the t-star for this would be 0.678. With the 95% confidence interval, it's basically 2. But if I change it and say I want the 60% confidence interval, you'll need to know how to obtain that. So that's how we get t-star whenever we're asked for t-star. T-star equals 1.98, which is approximately 2. And so you're right, Chelsea, in the notes it says 2, but we had to calculate that. And so rather than me just saying, okay, here's what it is, you guys will need to know for whatever confidence interval how to calculate it. After we have the t-star, we can calculate the confidence interval, and it's the formula that we just saw, and then go back and plug in the appropriate numbers, and we get our confidence interval for our point estimate. What we're wanting to know is, just being labeled a high achiever, will that have an effect on the student's IQ compared to if they didn't have that label? And so this is the confidence interval of the difference in change in IQ scores between the control group and that group that was labeled high achievers. And so based on this confidence interval, what can we conclude about being labeled a high achiever? You want to try, Rachel?
Well, I'm just confused. A couple slides back, you said something about 0. What did that have to do with?
Okay. We're looking at the difference between high achievers and the control group. This is the change in IQ score for high achievers, and this is the change in IQ score of control group. And so if there was no effect of being labeled a high achiever, then we would expect to see no difference in IQ scores, because you're just randomly picking people and taking their IQ score. But in our sample, we observed a difference of 3.8. This is our point estimate to make inferences about the whole population. But this is just a point estimate, and so if we redid the study, we might get a slightly different difference in means. So it might be something like 3.9 and 3.75. It will change each time. In order to make inferences, we need to know the confidence interval for this point estimate, where we can say that we're 95% confident that the population parameter falls within this range. With this, we see that we're 95% confident that it falls within the range of 0.17 to 7.43. So we're 95% confident that the difference in IQ scores is going to fall within this range. Yeah?
I understand that, but I don't get how to translate that into like whether or not there's actually, like this makes sense to me, but that it doesn't make sense how that tells you whether or not there's a difference. Like that just tells you that our value is within 95%, which is to be expected. That's where I'm getting lost.
A way to interpret this is we don't know if there is an effect. We don't have proof of whether or not there's effect of being labeled a high achiever or not, but we can run an experiment and take a sample, and the sample gives us a point estimate, but the point estimate has variability. Like if we did the experiment again, it might be slightly different. And so we'll establish a confidence level, and we'll say we want to be 95% confident that the population parameter falls within a certain range. If we ran this experiment 100 times, 95% of the outcomes, the difference in sample means, would fall within this range. And in this case, we're 95% confident that there is a difference, because the value of 0 isn't included in the confidence interval.
Okay.
So our confidence interval ended up being from 7.43 to negative 0.6. We wouldn't be able to say with confidence, with a 95% confidence, that the change in IQ scores is significantly different from 0.
Okay, so it's whether or not it's like above 0.
Yeah, basically it can only tell you yes or no. It can't tell you how often would you get the value 0. Is it super likely to get the value 0? It's either, is it in the confidence interval or is it not? If the confidence interval contains the value that would be representative of no effect, then you kind of have to say, well, this 3.8 that we got could have just happened by random chance, even if there was no effect. The way you interpret the results is that we're 95% confident that telling teachers a student will be a super high achiever increases the student's IQ score on average between 1.7 and 7.3 points after 1 year. Like we kind of know it's going to have some effect. It can vary between 0.17 and 7.43, but we know we're 95% confident that it's going to be greater than 0. The other way to do it is through a hypothesis test. Get all your summary statistics lined up. The first would be to state the hypotheses. So can someone take a stab at stating the null hypothesis? U sub 1 minus U sub 2 equals 0. Perfect. So then alternative hypothesis.
1 is greater than 2.
Mu sub 2. Okay. Perfect. So now when we're going to be checking if it's a right tail, left tail, or two tail test, we base it off of the alternative hypothesis. So based on this alternative hypothesis, what's the tail? What tail test are we going to do?
A right tail.
Why a right tail?
Because it's greater than.
Exactly. So we're looking at, like, if this is going to be our distribution, we're looking at the values that are larger than whatever our test statistic is. So we'll do right tail. You check the conditions to make sure that the sample size is large enough to make the assumptions about the distribution of the test statistic, and then calculating the test statistic using the formulas that we have. So we get a test statistic of 2.096, and then we need to find out what the p-value is for that test statistic. And how would we do that? So we go to stat key, and where do we go? What we've just calculated was a t-statistic. And so we want to know where that t-statistic falls on the t-distribution. So we look at the t-distribution, and then the degrees of freedom. Do you remember those, Timothy?
Would it be 64?
64, yep. Okay. What tail test are we doing? Right tail. How do we find the p-value for our test statistic? Okay. And our test statistic was 2.096. And so then our p-value for our test statistic is what? 0.02. We walk through the whole process. We have a p-value of 0.02, and what that's saying is the probability of getting a sample statistic as large as what we got, as large as 3.8, the probability of that is 0.02. So there's a 2% chance that we would get a sample statistic as large as 3.8 if the null hypothesis was true. How would we interpret that in light of our question of, does labeling someone a high achiever have an effect of increasing the student's IQ? What would be our conclusion or interpretation? Brittany says yes.
You reject the null in favor of the alternative hypothesis because your p-value, I mean, even if we had like a 0.05.
We would reject the null hypothesis, obtain a p-value of 0.02. So you can't just stop with, oh, it's 0.02, or, oh yeah, 0.02 is less than 0.05, so we reject the null. You have to interpret the number. And this says, this provides evidence that positive teacher expectations significantly increase student IQ scores. Or you could say, labeling a student a super high achiever will lead to higher IQ scores. What's interesting is the children in the study weren't even told that they were super high achievers. So it's just purely the way that the teacher interacts and relates to the students. A lot of times you stop at the point of, okay, here's the confidence interval or here's the p-value. You need to take it the final step as a sociologist and say, what is it that we actually can conclude from this study? So that was difference in means. The other thing is correlations. And correlations is also working with two quantitative variables. With all of these, what we want to know is how do you calculate the standard error for a particular sample statistic. And so for correlations, the way you calculate the standard error is 1 minus r squared over n minus 2, and you take the square root of the whole thing. And so where the challenge with formulas is, by faith, I trust that this is the formula. And by just knowing the formula can get things really confusing. And that's why in the first section of this class, we looked at the way to do it in a very mechanical or tactile way of doing bootstrap samples or the randomization sampling. Because you could see the distribution and you could actually see what the standard error for that distribution was. This way, it's just, I know there's probably some fancy mathematics behind how they arrived at this, and they're making assumptions that the sample statistic is going to be normally distributed, and so that's how they're able to arrive at this. But it'd be helpful if you kept clear in your mind that when we're talking about standard error, we're talking about the distribution of the sampling statistic. We want to know how much does our sample statistic vary, and that's what the standard error is telling us. It's telling us how much our sample statistic will vary from sample to sample. Sampling distribution for correlation also follows a t-distribution, and in this case, the degrees of freedom is n minus 2. So again, we do confidence intervals and hypothesis tests for correlations. And if n is large enough, or if the sample data are normally distributed, a confidence interval can be calculated by, hey look, it's the same formula. We have our sample statistic, our t-star, and our standard error. But again, the standard error for a correlation uses a unique formula. Our sample statistic is the correlation value, and then you have t-star, and then here's the equation for standard error. And so T star is the location on the T distribution with n minus 2 degrees of freedom, and its value is determined by the confidence level that's selected. So a lot of this is just the same process, and so clearly this is a process that you'll need to know how to do. Whatever's thrown at you, you'll be able to know, here's how I get all the important values that I need. For a hypothesis test, we want the distribution of the sample correlation. That should be, for the null hypothesis, that the correlation would equal the null correlation. And again, a lot of times the null correlation is 0, that there's no correlation, no association. Test statistic is the same as what we've used before. And then the difference is the standard error. The way of calculating the standard error for a correlation has its own equation. And then once you get the test statistic, you can obtain the p-value by looking at where it fits on the t-distribution. Remember, when you're looking at t-distribution, you need to input what the degrees of freedom are. Okay, so a specific example to walk you through this. We're going to look at age and religious attendance. So is a person's age correlated with how often they attend religious services? So we have two quantitative variables, age and frequency of attending religious services. So based on 2,033 respondents in the 2010 GSS study, the sample correlation between the respondent's age and how often they attend religious services is 0.14. So is this correlation significant? i.e., is it significantly different from 0? What are the two ways that we could answer this question? Brittany?
Confidence interval and hypothesis test.
Perfect. Well, it depends. If we're sufficiently confident that the confidence interval for the point estimate, which is 0.14, for the sample correlation does not contain 0, is the first approach, or it depends how likely it would be to get a sample correlation as large as 0.14 by random chance if the null hypothesis was true. So it's the same idea as if the confidence interval for that point estimate extends out and includes 0, then it's like we could rerun this study and find out that there is no correlation. And so there's a 95% likelihood that it would fall within that. If you're given a sample statistic, all that is a point estimate. And so then you need to do either a confidence interval or a hypothesis test to see if it's actually a significant effect that we're observing or a significant relationship. So we do confidence interval, we have our summary statistics up here, all this important information that we're given, and so then we need to check the conditions that the sample size be greater than 30, and then we find the t-star for a 95% confidence interval, which I think we've done, so it's equal to 2. We calculate the confidence interval using the formula that we have, and so making sure we put in the right equation for standard error. So then we see a correlation of 0.096 to 0.184. And so what can we conclude about whether or not there's a correlation between age and religious attendance? Brittany?
But there is a significant correlation.
Why?
Because the lower boundary is greater than 0.
Okay.
The 0 is not included.
Not included in the confidence interval. To formally say it is we're 95% confident that the correlation between a person's age and how often they attend religious services is between 0.096 and 0.184. That there is some correlation between age and religious attendance. To show you how it relates to the GSS, and what you'll actually be doing this in your research project. So if we go to the GSS, the first thing, because we're doing analysis, we go up to the analysis tab, and then you go over to the correlation matrix. And so then here you enter the two variables, and the two variables are age and attend. And then one new thing in this process, remember I said is we're just going to look at the 2010 survey. This will be an important thing for you guys to learn. There's a thing called filters. You start off looking at every survey and every variable, but you can put in filters to restrict what you're going to look at. And so in this case, we're going to do year is the name of a variable. And so you say, I only want to look at the values that are in year 2010. I'm going to click on here, the standard errors of correlations, and that will tell us what the standard error for our correlation is. And then we'll run the correlation, and it pops up in here. This is what we were given, the correlation of 0.14, and what we calculated was the standard error of 0.022. And so at the end of the day, you won't have to calculate standard errors, but in order to know where you're getting this number and what it means, we'll have to calculate it. But you can check yourself by seeing, did I do the math right? And so on GSS, it shows you what the standard error is. And the standard error is 0.022. We'll walk through the hypothesis test for correlations. So can someone else do the null hypothesis for this particular test? We're wondering if there's a correlation between religious attendance and age. And we always put hypothesis in terms of population parameters. So it's rho, which is capital R in Greek. Our sample statistic is that R equals 0.14. The correlation of 0.14. And so the null hypothesis is saying that there's no association or no correlation. And the null hypothesis would say that rho, which is the population correlation, equals what?
0.
Equals 0. So it's saying that there is no correlation. And then what would the alternative hypothesis be?
Rho is greater than 0.
Okay. So rho is greater than 0. Good. Would this be right tail, two tail, or left tail? Chris?
Right tail.
Right tail. So you can either say not equal 0 or greater than 0. It just depends how you want to set up the alternative hypothesis. And you check the conditions, you calculate the test statistic. So we get a t statistic of 6.36. How do we find out the p-value from the test statistic? Stat key. By the way, you can't just write on the exam stat key.
That won't work.
That won't work. Okay, we're at stat key, and then what do? We have our t statistic, and we want to know where it fits on the t distribution.
T.
Okay, t, our degrees of freedom, it's 2031. And then what do?
Right tail.
Right tail
Change the 1.961.
to 6.36. What's our p-value? 0. So how do we interpret this p-value? We're wondering if there is a correlation between a person's age and religious attendance. What does this p-value tell us? What is the probability that we would observe a correlation as large as 0.14 if the null hypothesis was true, if there was no relationship? And they're like, if there was no relationship, the probability of getting a correlation of 6.36 is like basically 0. Like you would never get a correlation as large as what we got if the null hypothesis was true. So we can reject the null hypothesis and accept the alternative hypothesis, which says that there is a correlation between religious attendance and age. Again, this provides very strong evidence that people increase the religious attendance as they get older. The difference between a confidence interval and a hypothesis test, with the confidence interval, you just know does it contain the value or not. The hypothesis test lets you know how strong your evidence is. What's the likelihood that you would get a sample statistic as extreme as the one we got? Just so you can have in your notes, we've done it. We've gone through the 4 lectures of how do you calculate all these statistics based on the normal distribution. So that is all.